In these problems, we are being asked to find a definite integral. And if you haven't run into this before, there's a lot to learn. There's some different looking notation. This is the notation for a definite integral. That big stretched out S thing is the integral sign, and then our interval, it's a definite interval because it's integral because it's on an interval from 0 to 3. And what we're really finding here, the number we find, is going to be the area under the curve of this function, negative 14/3 x squared. So we've dabbled a little bit in that sort of thing. You might remember trying to approximate the area under a curve by drawing these rectangles and calculating their areas and adding them all together. Here in the ALEKS explanation for this problem, it's got kind of a nice graphic here about how you can reduce the overestimation of this kind of a thing by making more thinner rectangles. And what we're actually going to try to do here with this definite integral is use a limit of a sum to make the number of rectangles go to infinity and be infinitely skinny. Because if that's the case, if the rectangles are infinitely skinny and infinite in number, they'll fit perfectly under that curve and we'll get the exact number for the area. And believe it or not, we can actually do this. It just requires a fair amount of algebra to do. Let me walk you through the sum notation here. So this says we're going to find the limit as n approaches infinity of this sum starting with I equals 1 up to n of our function f of x sub I. So all of these represent the endpoints of the rectangles, the heights of the rectangles, at times delta x. And delta x represents the width of the rectangle. So in this case, to get the width of the rectangle, we're going to take the width of our interval, which is from 0 to 3 here. That's 3 wide, and put that over n, because the width of the whole thing divided by the number of rectangles is going to get you the width of a rectangle. So this goes in here. Okay. What goes in here is our function, because that's going to give you the height there of the rectangle. So we're going to have negative 14/3 times x sub I squared, and then times that delta x, the width of the rectangle, is 3 over n. Now, x sub I, we can write in a different way too. Where is x sub I going to be? If you think about those rectangles, x sub I, the x value you put in here, is going to be one rectangle's width away from the starting point, or at least the first one is. So we can think about this as using this. Well, our starting point is 0. If your starting point on your interval was some other number, you'd have to put that in there. So we have our starting point plus the width of our rectangle. And then for any rectangle, it's just going to be times I. So for the first rectangle, 1 times 3 over n is how far away from our starting point it is. For our second rectangle, 2 times 3 over n is how far apart it is from the beginning. So when we write that, I'll leave off the 0, but you can't leave off the number if it's some number other than 0. So now we've got negative 14/3. And in here, instead of x sub I, I've got I times 3 over n. And this is all squared because that's part of the function. It's negative 14/3 x squared. And we've still got our 3n. And of course, we're still trying to make a sum here from I equals 1 to n. Now, what we need to do here is we need to isolate I. So we're going to use algebra to do that. The reason we're trying to do that is because we've got these handy formulas up here that tell us the sum of the first positive integers for I, or the sum of the first positive integers for I squared, so squares of the first positive n integers. So this is a method. These formulas are a method to rewrite I in terms of n. And then so we're trying to find the limit as n approaches infinity. That's going to be very helpful for us. So let's try to isolate I here. Let's see. Well, we're going to square what's inside first. So that is I squared and 9 over n squared. And then out here we've got 3 over n. And all of this stuff is multiplied together. So we can, well, this will cancel. Make sure that's an I, not a 1. And then we've got negative 14 times 9, that's negative 126. And then I've got, let's bunch up these together. So that's basically, so that's over n cubed. Yeah, so over n cubed. And then I've got my I squared hanging out there. So the 9 and the negative 14 made the negative 26, the n squared and the n made the n cubed, and we left the I alone. Now the reason I did that is because this is a sum, and a sum, this part right here, negative 126 over n cubed, that's just a number. N is always a number. So this part can be taken and put out front. You multiply some number by the whole sum, it's the same as multiplying it by each element of the sum. It's the same thing, it's just the distributive property. So I can write this as negative 126 over n cubed, and times the sum from 1 to n of I squared. Now I can use this formula here. So this is what that sum of the I squared is going to change into. So this part right here, I still have my negative 126 over n cubed, but this is going to be multiplied by that expression n times n plus 1 times n, 2n plus 1 all over 6. Let's see, let's multiply that out. We're going to get, I'm going to save time here, 2n cubed plus 3n squared plus n over 6. If you don't believe that's the case, go ahead and take the time to do that on your own. Negative 126 over n cubed. And now we're going to multiply and divide by 6. Let's see, 126 divided by 6 is 21. So that's going to be a negative 42 n cubed minus 63 n squared minus 21 n, and all of that is going to be over our n cubed. This is looking good. Now, the n cubed, let's write these as separate terms. So negative 42 n cubed over n cubed is just negative 42. Negative 63 n squared is, so minus 63 over n, canceling the n's there, and then minus 21 over n squared. So we wrote the sum in terms of n. Originally, we wanted to take the limit of the sum, so we need to take the limit of this as n approaches infinity. And finally, it's in a form where we can do that. If we put infinity at the bottom of a fraction, these things approach 0, and we can ignore them, and our answer ends up being negative 42. So the area under that curve on the interval 0 to 3 was negative 42. How is it a negative number? Well, that's how it registers if the curve is below the x-axis as a negative number. So that was a lot. I went through that pretty quickly because I'm on a 10-minute time limit on my recording device. So feel free to slow that down, go back, look it over again. Pretty complicated stuff. But that's how to evaluate a definite integral using a limit of a sum.